You're staring at your computer screen at 3 a.m., scrolling through the latest astronomical data when something stops you cold. The numbers don't make sense. An object, no. A visitor is hurtling through our solar system at speeds that defy everything we know about natural celestial mechanics. It's not slowing down. It's not following the rules. And in just weeks, it will dive straight into the heart of our sun. Scientists are watching. Governments are monitoring. But the public most have no idea that something far more mysterious than the infamous Oumuamua, or 3I/Atlas, is currently racing toward the most dramatic cosmic encounter of our lifetime. This isn't science fiction. This is happening right now. And what we discover in the coming days could rewrite our understanding of what's really out there in the darkness between stars. If you're as fascinated by cosmic mysteries as I am, and you want to stay updated on discoveries that mainstream media often overlooks, hit that subscribe button and ring the bell, but only if what you're about to learn genuinely captures your curiosity. A quick like helps more people discover these stories too. Now, let's turn down the lights and dive into something extraordinary. You pull up the data stream from the Pan-STARRS telescope in Hawaii, one of humanity's most vigilant eyes on the sky. It's March 2024, and something has just triggered the automated detection system. At first glance, it looks like another routine asteroid, another piece of cosmic debris wandering through our celestial neighbourhood. But as you start plotting its trajectory, your coffee goes cold in your hand. The orbital path doesn't close, it doesn't loop. It's a hyperbola, a one-way ticket through our solar system. Your colleague across the lab notices your expression. "What have you got?" she asks, leaning over your shoulder. You point at the screen. "This thing isn't from here, and it's moving fast." Here's what makes your heart race. Most objects in our solar system follow elliptical orbits, bound by the sun's gravity like runners on a cosmic track. They go around and around. Predictable. Calculable. Safe. But this object, it's got what astronomers call excess hyperbolic velocity, meaning it's carrying more speed than the sun's gravity can explain. It came from somewhere else. And it's not planning to stay. The designation comes through official channels within our C2024 G3 Atlas. The C tells you it's a comet. The 2024 G3 marks it as the third object discovered in early April 2024. And that Atlas at the end, that's the telescope system that caught it first, the Asteroid Terrestrial Impact Last Alert System, a network specifically designed to find things that might pose a threat to Earth. But here's where it gets interesting. You run the numbers again, triple check in because what you're seeing seems almost impossible. This object is travelling at roughly 290,000 miles per hour relative to the Sun. To put that in perspective, that's about 400 times faster than a rifle bullet. At that speed, you could travel from New York to Los Angeles in less than 90 seconds. Earth's escape velocity, the speed needed to break free from our planet's gravity, is about 25,000 miles per hour. This visitor is moving more than 10 times that speed. You scroll through the preliminary observations. The object's brightness is fluctuating, which suggests it's either irregularly shaped, tumbling through space, or actively venting gas and dust as it heats up approaching the inner solar system. Or maybe all three. Amateur astronomers around the world are already picking it up in their backyard telescopes, sharing images on forums and social media. One astronomer in Australia comments, "This thing's getting brighter way faster than the models predicted. Something's not adding up." And he's right. When you compare C2024 G3 to typical long-period comets, those icy wanderers from the Oort cloud at the edge of our solar system, the numbers diverge. Long-period comets usually approach the Sun at around 100,000 to 150,000 miles per hour. This object is nearly double that. The orbital eccentricity, a measure of how elongated an orbit is, comes back at 1.00034. Anything above 1.0 means the orbit is unbound, open-ended, hyperbolic. This visitor punched through our solar system's boundary and it's not turning back. You pull up the trajectory projection. The software calculates its path backward, tracing where it came from. The computer churns through the math, accounting for the gravitational influences of Jupiter, Saturn, and the Sun itself. The result makes you sit back in your chair. If you rewind this object's journey thousands of years into the past, its origin point lies somewhere in the direction of the constellation Ophiuchus, roughly toward the galactic plane. It's been travelling through the void between stars for longer than human civilization has existed. Doctor. David Farnokia from NASA's Center for Near-Earth Object Studies would later tell reporters, "What we're seeing with objects like this challenges our understanding of what's normal in our cosmic neighbourhood. Every interstellar visitor we detect gives us a glimpse into the diversity of planetary systems beyond our own." But here's what keeps you up at night: the perihelion date. January 13th, 2025. That's when C2024 G3 will make its closest approach to the Sun, a mere 8.3 million miles from our star's surface. For context, Mercury orbits at about 36 million miles from the Sun, and even that scorched little planet experiences temperatures hot enough to melt lead. This object is going to pass 4 times closer than Mercury, diving through temperatures exceeding 3600 degrees Fahrenheit. You remember what happened to Comet Ison in 2013? Astronomers called it the Comet of the Century before its close solar approach. Ison came within 730,000 miles of the Sun's surface, still much farther than where C2024 G3 is headed, and it disintegrated completely. The Sun just tore it apart. You watch the archived footage of Ison's death. One moment it's visible in NASA's SOHO spacecraft images. The next it's just a fading smudge of dust. Will C2024 G3 suffer the same fate? Or is it made of sterner stuff? The spectroscopic data starts coming in from observatories worldwide. The light signature shows evidence of water vapour, carbon dioxide, and carbon monoxide, typical comet stuff. Frozen volatiles from the formation of some distant planetary system. But there's something else in the data. Anomalous emission lines that don't quite match the standard comet profile. Could be exotic ices, could be unusual mineral composition, or could be something no one's ever seen before. Your colleague returns with fresh coffee. So what's the verdict, natural snowball from another star system? Or should we be calling Jodie Foster? She's joking, referencing the movie Contact. But there's a thread of genuine curiosity in her voice. Because here's the uncomfortable truth that astronomers don't often say out loud: we genuinely don't know everything that's possible out there. We've only been seriously studying interstellar objects since 2017. We're cosmic toddlers trying to understand the neighbourhood. You save your calculations and lean back. Right now, all the data says natural comet, but we've got 2 months of observations ahead before perihelion. If this thing does something weird, changes velocity without outgassing to explain it, sends out radio signals, deploys solar panels, then we'll have a very different conversation. She laughs. But you notice she's looking at the trajectory plot with the same mix of fascination and unease that you feel. Because the truth is, C2024 G3 is already doing something weird. Its brightness curve doesn't match the models, its approach velocity exceeds expectations, and it's heading toward a cosmic crucible that will either destroy it completely or reveal exactly what it's made of. In just 87 days, we'll have our answer. But before we watch this drama unfold at the Sun, We need to talk about the visitors that came before, because C2024 G3 isn't the first mysterious object to crash our solar system's party uninvited. And understanding what happened with those previous encounters might be the key to decoding what's racing toward us right now. October 19th, 2017. Robert Verick, a postdoctoral researcher at the University of Hawaii, is doing what astronomers do best, staring at data that would make most people's eyes glaze over. He's reviewing images from the Pan-STARRS 1 telescope, the same system that would later spot C2024 G3. But on this particular night, Verick notices something that makes him do a double take. There's a faint streak of light moving across the starfield, and when he calculates its trajectory, his stomach drops. The object is moving at 54 miles per second, that's 196,000 miles per hour. But here's the kicker, it's moving away from the sun, and it's already past Earth's orbit. He runs the calculations backward. This thing came from the direction of the constellation Lyra, swooped through our inner solar system at a sharp angle, whipped around the sun, and is now headed back out into deep space. The orbital eccentricity 1.20, wildly hyperbolic. Verick immediately alerts the Minor Planet Center, the astronomical clearinghouse for such discoveries. Within days, observatories worldwide are scrambling to track this cosmic interloper before it fades from view. They give it a designation that will become famous, 1/2017 U1. The I stands for interstellar, the first object ever officially classified as a visitor from beyond our solar system. But it's the Hawaiian name that captures public imagination, Oumuamua, meaning scout or messenger from the distant past. And boy, did it have a message, one that scientists are still arguing about today. Here's where things get weird. As telescopes around the world focused on Oumuamua, they discovered something that didn't make sense. The object was shaped like nothing they'd ever seen before. Initial observations suggested it was 10 times longer than it was wide, like a cosmic cigar or a giant space cucumber. If you want to get technical, later analysis suggested it might be more pancake-shaped, like a cosmic frisbee. Either way, you don't see natural objects shaped like that. Asteroids and comets are usually lumpy, potato-like. This thing looked designed. Dr. Karen Meach from the University of Hawaii, who led some of the initial observation teams, described it as unlike anything we've seen in our solar system. That's astronomer speak for, what the heck is this thing? But the shape was just the beginning. As Oumuamua travelled away from the sun, something even stranger happened. It accelerated. Not much, just a tiny, almost imperceptible push, but it was definitely speeding up. Now, comets do this all the time. As they heat up near the sun, frozen gases turn into jets of vapour that act like little rocket engines. It's called outgassing, and it's perfectly normal. Except Oumuamua showed no signs of outgassing, no tail, no coma, that fuzzy cloud of gas and dust that surrounds active comets. No spectroscopic evidence of water vapour or any other volatiles venting into space. It was accelerating without any visible means of propulsion. Imagine watching a car roll uphill without an engine running, without anyone pushing it, without any explanation at all. That's essentially what astronomers were witnessing. The scientific community split into camps faster than you can say peer review. Most astronomers argued for exotic but natural explanations. Maybe it was made of frozen hydrogen that vaporized invisibly. Maybe it was venting from a narrow jet we couldn't see. Maybe it was experiencing some kind of thermal effect we didn't fully understand. All valid scientific speculation. But then there's Professor Avi Loeb. Loeb, chair of Harvard's astronomy department and one of the most cited scientists in his field, looked at the same data and reached a different conclusion. In 2018, he co-authored a paper that sent shockwaves through both the scientific community and popular media. His argument: the simplest explanation for Oumuamua's behaviour is that it's artificial, specifically a light sail, a thin reflective sheet pushed by solar radiation, technology that humans are already developing. The excess acceleration of Oumuamua, Loeb wrote, is consistent with a thin object with a large surface area to mass ratio. In other words, exactly what you'd expect from a spacecraft sail. The backlash was immediate and fierce. Many of Loeb's colleagues accused him of sensationalism, of jumping to extraordinary conclusions without extraordinary evidence. One astronomer called it a shocking example of sensationalist, ill-motivated science. The scientific Twitter sphere, yes, that's a thing erupted into arguments that got surprisingly personal. But here's what makes Loeb's position interesting. Regardless of whether you agree with it, he's not claiming little green men, he's making a statistical argument. If even a tiny fraction of the billions of technological civilizations that might exist in our galaxy sent out probes, then interstellar space should be filled with them, and occasionally, one should pass through our solar system. The odds might actually favour artificial objects over natural ones. Loeb told reporters, in science, we must remain open to all possibilities, especially when the evidence doesn't fit our expectations. Dismissing the artificial hypothesis without proper investigation would be a disservice to the scientific method. Whether you think Oumuamua was a space probe or an exotic comet, one thing became crystal clear: we were completely unprepared for it. By the time astronomers realised what they were looking at, Oumuamua was already leaving. We got about 11 days of decent observations before it became too faint to study. No spacecraft could reach it. No detailed spectroscopy. No close-up images. Just a handful of data points and a whole lot of questions. Think about that for a moment. Humanity's first confirmed encounter with an interstellar object, and we basically watched it drive by, waving frantically from the sidewalk, unable to chase it down. It's like if aliens landed in your backyard. But by the time you grabbed your phone to take a picture, they'd already left, and all you're left with is some weird marks on the grass and your family asking if you've been getting enough sleep. The experience humbled the astronomical community. NASA immediately started discussions about how to better prepare for the next interstellar visitor. The European Space Agency proposed mission concepts for rapid response spacecraft that could intercept such objects. Because one thing was certain, Oumuamua wouldn't be the last visitor from beyond. They had no idea how right they were, or how soon the next one would arrive, bringing with it behaviours that would make Oumuamua look downright normal by comparison. You don't have to wait long. Less than 2 years after Oumuamua's flyby, another interstellar visitor comes knocking. This time, though, there's a crucial difference. We catch it before it reaches its closest approach to the Sun, giving astronomers an actual chance to study it properly. August 30th, 2019. Gennady Borisov, a Crimean amateur astronomer using a telescope he built himself in his backyard, spots something unusual. And when we say backyard telescope, we're not talking about a department store refractor. This is a serious 0.65 metre instrument that Borisov engineered specifically for hunting comets. The man knows what he's looking for. The object gets designated 2I/Borisov Humanity's second confirmed interstellar visitor. And right away, you can tell this one's different from Oumuamua. For starters, it actually looks like a comet. It's got a tail, it's got a coma, it's venting gas and dust in a completely normal, predictable way. Scientists breathe a collective sigh of relief. Finally, something that makes sense. But here's where 2I/Borisov gets interesting in its own right. As observatories worldwide track this cosmic traveller, they discover it's not just any comet, it's one of the most pristine examples of a comet ever studied. The spectroscopic analysis shows it contains cyanide gas and diatomic carbon at concentrations higher than anything we've seen in solar system comets. This thing is ancient, perhaps preserving chemistry from the formation of its home star system billions of years ago. Doctor. Martin Cordiner from NASA's Goddard Space Flight Center called it the most primitive comet we've ever examined. It's like a time capsule from another planetary system. Now, you might be thinking, wait, if 2I/Borisov was so well behaved, why did you say it made Oumuamua look normal? Patience. Friend, we're getting there. Fast forward to late 2024. The Atlas survey system, yes, the same one that found C2024G3 picks up another anomalous object. Initial designation A2024L5. That A prefix is telling. It means astronomers aren't sure what it is yet. Not quite a comet, not quite an asteroid, something in between. Within weeks, as more observations roll in, something becomes clear: this object is fragmenting. Not in the explosive, dramatic way that some comets break apart, but in a slow, unsettling disintegration. Pieces are carving off the main body like icebergs from a glacier, and the trajectory hyperbolic. Eccentricity of 1.0002. The astronomical community gives it a new designation to reflect its interstellar origin 3I/Atlas. The third confirmed visitor from beyond our solar system, and it's falling apart before our eyes. Doctor. Teddy Coretta from Lowell Observatory watches the disintegration through one of the most powerful telescopes on Earth. What we're seeing is consistent with a loosely bound rubble pile that's being torn apart by solar radiation and tidal forces. He explains in a webinar you're watching at 2 a.m. because, let's face it, sleep is overrated when cosmic mysteries are unfolding in real time. But here's what keeps you glued to that webinar: the fragmentation pattern doesn't match standard models. Typically, when comets break apart, they do so in predictable ways based on structural stress points and rotational forces. 3I/Atlas is fragmenting asymmetrically, with pieces breaking off in ways that suggest an irregular internal structure. Some fragments are venting gas, others aren't. Some are accelerating slightly, others are staying on course. You pull up the data feed from the Hubble Space Telescope. NASA allocated precious observation time to image 3I/Atlas because, well, when an interstellar object is actively disintegrating, you don't pass up that chance. The images show at least 4 distinct fragments, each following slightly different trajectories as they orbit the Sun. It looks less like a comet breaking up and more like a cluster of objects that were loosely bound together flying apart in slow motion. Amateur astronomer forums light up with speculation. Could this be a shattered moonlet from another star system, one user asks? Maybe a collision in a distant asteroid belt sent debris our way? Another suggests. The ideas range from scientifically plausible to delightfully creative. Someone proposes it's an alien spacecraft that suffered a catastrophic failure millions of years ago. Its wreckage now tumbling through the galaxy. You have to admit, the mental image is kind of haunting. But the professional astronomers are asking different questions. Doctor. Michelle Bannister from the University of Canterbury points out something crucial. The fact that we're seeing multiple interstellar objects in just a few years suggests they're far more common than we thought. We're not witnessing rare events, we're witnessing the tip of the iceberg. Think about that for a second. Before 2017, the confirmed count of interstellar objects passing through our solar system was 0. By 2024, it's 3. And those are just the ones we detected. Statistical models now suggest that at any given moment, there might be dozens of interstellar objects cruising through our solar system, most too small or too far away for our telescopes to spot. One study published in the Astronomical Journal estimated that Oumuamua-sized objects pass through the inner solar system at a rate of about 1 per year. Smaller objects, thousands per year. Larger ones, maybe 1 per decade. We've been living in an interstellar shooting gallery this whole time and never knew it. You download the orbital data for all 3 confirmed interstellar visitors and plot them on your screen. Oumuamua came from the direction of Vega, passed through at a steep angle, and left toward Pegasus. 2I/Borisov came from the direction of Cassiopeia and departed toward Telescopium. 3I/Atlas approached from near the ecliptic plane and is currently heading. Actually, nobody's entirely sure where the fragments are heading because they're all on slightly different paths now. There's no pattern, no common origin point. These objects are coming from completely different directions, suggesting they've been wandering the galaxy for unimaginable stretches of time, each one a messenger from a different stellar neighbourhood, carrying information about planetary systems we'll never visit. And now, here you are, watching the data stream for C2024G3, wondering what story this visitor is about to tell. Because if there's one thing the previous interstellar objects taught us, it's that each one is full of surprises. Each one breaks our expectations in new and unsettling ways. But C2024G3 isn't like any of them. It's faster. It's heading for a closer solar encounter. And unlike its predecessors, we're going to watch it dive into the sun's inferno in real time, with every major telescope on Earth and in space trained on it. Whatever happens in the next few weeks won't be a mystery glimpsed in fragmentary data. It'll be the most observed interstellar event in human history. So let's talk about C2024G3 Atlas, the object currently sprinting toward the sun like it's got somewhere urgent to be. Because unlike its interstellar predecessors that we watched fade into the distance, this one is racing toward the cosmic fireworks display of a lifetime. You're monitoring the updated observations coming from observatories across the globe. It's December now, and C2024G3 has crossed Mars's orbit, currently somewhere between the red planet and Earth. With each passing day, it's getting brighter, easier to spot, and more puzzling. The first thing that strikes professional astronomers is the sheer velocity. We mentioned the 290,000 miles per hour figure earlier, but let's put that into a context that really hits home. The New Horizons probe, the fastest spacecraft ever launched from Earth, travelled to Pluto at about 36,000 miles per hour. C2024G3 is moving 8 times faster than that. If we wanted to catch up to this thing with current technology, we'd need to invent an entirely new form of propulsion, and probably violate a few laws of physics while we're at it. Dr. Kwanji Ye from the University of Maryland has been tracking C2024G3 since its discovery. In a recent interview, he said something that made your coffee taste a little more bitter than usual. The approach velocity alone tells us this object has been travelling through interstellar space for potentially millions of years. What we're witnessing is the endpoint of an unimaginably long journey. Millions of years. Let that sink in for a moment. While this object has been hurtling through the void between stars, Earth has seen the entire rise of human civilization, from the first stone tools to smartphones. And now, purely by chance, its trajectory intersects with our solar system at this exact moment in cosmic history. But velocity is just the opening act. You pull up the brightness data, and this is where things get genuinely strange. Most comets follow a predictable brightness curve as they approach the sun. They get steadily brighter following a mathematical relationship that astronomers have understood for centuries. It's called the inverse square law: get twice as close, get 4 times brighter. Simple physics. C2024G3 doesn't care about your simple physics. The brightness measurements show irregular spikes and dips that don't match the smooth curve they should. One night it's magnitude 9, too faint for the naked eye but easy in binoculars. 3 nights later it's jumped to magnitude 7.5, then dropped back to 8.2, then spiked to 7. It's fluctuating like a cosmic disco ball, and nobody's quite sure why. Amateur astronomer Michael Jaeger in Austria has been photographing the comet almost nightly, weather permitting, and he's documented something fascinating. In his images, you can see the coma isn't symmetric. Most comets develop a roughly spherical cloud of gas and dust around their nucleus. C2024 G3's coma is lopsided, with jets of material streaming off at odd angles. It's venting gas preferentially from one side, which means the nucleus is either spinning in an unusual way or has an irregular surface where volatile ices are concentrated in specific areas. It's like watching a cosmic lawn sprinkler that's broken, Jaeger writes in his observation log. You appreciate his analogy. Sometimes the best descriptions come from people who spend their nights actually looking at the sky rather than just analysing data. Here's where the numbers get truly unsettling. Using spectroscopy, astronomers can identify what gases the comet is releasing. Water vapour check, that's standard. Carbon monoxide present in higher quantities than expected. Cyanide, yep, also there, which sounds scary but is actually pretty normal for comets. They're dirty snowballs full of stuff that would absolutely kill you, which is why you should never lick a comet. File that under common sense advice that probably doesn't need saying, but here we are. But there's also methane, ammonia, and ethane showing up in the spectroscopic data, a cocktail of frozen volatiles that suggests this comet formed in an extremely cold environment. We're talking temperatures barely above absolute zero. These are the kinds of ices you'd expect from objects that formed in the outer reaches of a planetary system, perhaps even beyond what would be that system's equivalent of our Kuiper belt. Doctor Rosemary Pike from the Royal Observatory in Edinburgh points out something crucial. The chemical composition we're seeing is consistent with formation in a very young, very cold protoplanetary disk. This object might be a pristine remnant from the birth of another star system, chemically unchanged for billions of years. Think about what that means. You're looking at matter that hasn't been altered since another sun was born, somewhere out there in the galaxy. It's like finding a sealed time capsule, except instead of photos and newspapers, it's frozen gases that remember what the universe was like before Earth even existed. Now let's talk about that perihelion date, January 13th, 2025. Mark your calendars, because this is when C2024 G3 passes just 3 million miles from the Sun's photosphere. To give you a sense of scale, the Sun's diameter is about 865,000 miles. This comet is going to pass within about 10 solar diameters of our star's surface. You run the thermal calculations. At that distance, the Sun's radiation will heat the comet's surface to approximately 3600 degrees Fahrenheit, hot enough to melt copper, hot enough to vaporize most ices instantly, hot enough to potentially shatter rock. The comet will be exposed to this inferno for several hours as it whips around the Sun at peak velocity. But here's the really wild part: the timing is almost perfect for observation. The perihelion occurs when the comet is visible from Earth, and multiple space-based observatories, including the Solar and Heliospheric Observatory SOHO and NASA's Parker Solar Probe, will have direct lines of sight. The James Webb Space Telescope has even allocated observation time, which is like getting a reservation at the most exclusive restaurant in the universe. When JWST says yes to your request, you know something special is happening. Ground-based observatories from Chile to Hawaii to the Canary Islands are coordinating their observations. Amateur astronomers are planning viewing parties. YouTube channels are scheduling live streams. Everyone wants to see what happens when an interstellar visitor meets the sun face to face. Will it survive? Will it fragment? Will it put on a show that makes other comets look like birthday candles? The suspense is genuinely killing the astronomical community, and we've still got weeks to wait. But before we watch this cosmic collision unfold, there's something crucial we need to understand: what actually makes an object interstellar versus just a really eccentric solar system native. Because the math behind that distinction is where the real detective work happens, and it's how we'll know for certain whether C2024 G3 is truly the alien visitor it appears to be, or something far stranger. Imagine you're a cosmic detective, and you've just found a mysterious object wandering through your neighbourhood. The first question you need to answer is, does this belong here? Or is it a stranger from another town in astronomy? That question comes down to orbital mechanics, the math that governs how objects move through space. You open up the orbital calculation software that astronomers use, a program with the delightful name JPL Horizons, maintained by NASA's Jet Propulsion Laboratory. It's essentially a cosmic GPS system that can track anything in the solar system with ridiculous precision. You plug in the observation data for C2024 G3 position coordinates, velocity vectors, timestamps from multiple observatories. The software churns through the calculations, accounting for the gravitational pulls of the Sun, Jupiter, Saturn, and every other significant mass in our solar system. What comes back is a number that makes your pulse quicken. Orbital eccentricity equals 1.00034. Now, if you're not an orbital mechanics nerd, and let's be honest, most people aren't, that number might not mean much. So let's break it down in a way that actually makes sense. Every orbit has an eccentricity value between 0 and infinity. A perfect circle has an eccentricity of exactly 0, think of Earth's orbit, which is nearly circular at 0.0167. An elongated ellipse, like a comet from the Oort cloud, might have an eccentricity of 0.9 or 0.99 really stretched out, but still a closed loop. The object goes around the Sun and comes back, maybe in thousands of years, but it comes back. But when that eccentricity hits exactly 1.0, something fundamental changes. The orbit becomes a parabola, the mathematical borderline between trapped by the Sun and free to leave forever. It's like reaching escape velocity. And anything above 1.0, that's a hyperbola, an open curve that never closes. The object comes in, swings around the Sun exactly once, and heads back out into interstellar space, never to return. C2024 G3's eccentricity of 1.00034 means it's travelling on a hyperbolic trajectory. It's not bound to our Sun, it's just passing through. But here's where it gets tricky, and this is what keeps astronomers up at night arguing in academic journals. How do you know for sure that excess velocity isn't just from gravitational assists within our own solar system? Maybe this object started out in a normal elliptical orbit, got a gravity boost from Jupiter, then another kick from Saturn, and now it's moving fast enough to escape. That happens, it's called gravitational slingshot, and it's how we send spacecraft to the outer solar system. You run the calculations backward. If C2024 G3 were a solar system native, where could it have come from? The software traces possible trajectories, accounting for every planetary encounter that could have accelerated it. And here's what you find: there's no plausible scenario that works. For this object to have originated in our solar system and gained its current velocity through gravitational assists, it would need to have passed unreasonably close to Jupiter at exactly the right angle, multiple times without anyone noticing. The odds are astronomical, and not in the good way. It's technically possible in the same way that it's technically possible for every air molecule in the room to spontaneously move to one corner, leaving you to suffocate. The math allows it, but reality doesn't cooperate. Doctor. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics explains it this way. When we see hyperbolic orbits with excess velocities this high, and backward integration shows no plausible solar system origin, we're looking at an interstellar interloper. The evidence is about as solid as you can get in astronomy. So you trace the orbit further back. The software projects C2024G3's path into the past, before it entered our solar system, before it felt the sun's gravity, back when it was just drifting through the galaxy. The trajectory points toward a region of sky near the constellation Ophiuchus, angled slightly above the galactic plane. Here's where it gets wonderfully, terrifyingly vast. You calculate the object's velocity relative to the local standard of rest. That's the average motion of stars in our galactic neighbourhood. C2024G3 is moving at about 67 kilometers per second relative to that reference frame. That's its true speed through the galaxy, roughly 150,000 miles per hour. At that velocity, how long has it been travelling? You make some assumptions about its point of origin. If it came from a star system 50 light-years away, which is relatively close, in galactic terms it would have been travelling for over 500,000 years. That's before modern humans left Africa, before Neanderthals went extinct, before the last ice age even began. If it came from farther away, say 500 light-years, we're talking about a journey of 5 million years. Dinosaurs still walked the Earth when this object began its voyage. The entire genus Homo, every human species that ever existed, evolved during its flight through the void. You lean back and stare at the screen. This frozen chunk of primordial ice and rock has been wandering through the galaxy longer than your entire evolutionary lineage has existed. It's witnessed the birth and death of stars you'll never see. It's passed through molecular clouds, survived radiation from supernova shockwaves possibly, drifted through regions of space where the nearest star is so distant that the night sky would be almost perfectly black, and now, by pure cosmic coincidence, its path intersects with our tiny solar system at this exact moment. The odds of that happening are infinitesimally small, which is precisely why astronomers are now convinced that interstellar objects must be common, because if they were rare, we'd never see any. A study published in Nature Astronomy in 2023 estimated that there could be thousands of interstellar objects in our solar system at any given time. Most smaller than a few meters across. Bigger ones, like C2024G3, maybe a handful per year pass through the inner solar system, but only a tiny fraction are on trajectories that make them detectable with current technology. Think about that for a second. Right now, as you're reading this, there are probably dozens of visitors from other star systems cruising through our cosmic neighbourhood. Most are too small, too dark, or in the wrong place for us to spot them. We're like people living in a busy city but only noticing the occasional loud car that drives past our house. The neighbourhood is way busier than we realise. Doctor. Amaya Morrow-Martin from the Space Telescope Science Institute puts it bluntly. We're probably swimming in interstellar debris. The question isn't whether these objects are here, it's how good our detection systems need to be to find them. You save your calculations and pull up the live tracking data again. C2024G3 is now just weeks away from its solar close approach, currently passing through the inner solar system faster than anything humanity has ever launched. Every day it gets closer to that January 13th date, when it will either survive its encounter with the Sun as one of the most spectacular comets in recent memory, or disintegrate into a cloud of cosmic dust. its billion-year journey ending in fire. But what actually happens when an object travelling this fast, carrying this much frozen, volatile material, plunges into the sun's outer atmosphere? The physics involved are extreme, violent, and absolutely mesmerising, and we're about to witness them firsthand. Let's paint a picture of what January 13th, 2025 is going to look like from C2024 G3's perspective. You're a frozen chunk of ice, rock, an exotic chemistry that's been drifting through the absolute cold of interstellar space for eons. The background temperature out there. About 2.7 Kelvin, that's negative. 454 degrees Fahrenheit, just barely above the coldest temperature physics allows. For millions of years, you've been perfectly preserved in this cosmic freezer. Then, over the course of just a few months, you fall toward a star that's outputting 380 trillion watts of energy every single second. The temperature gradient you're about to experience is more extreme than anything most objects ever encounter. Let's run the numbers. Right now, in early December 2024, C2024 G3 is somewhere around 100 million miles from the Sun. At that distance, solar radiation is heating its surface to maybe negative 100 degrees Fahrenheit, cold enough to keep most ices solid, but warm enough that the most volatile compounds like carbon monoxide are starting to sublimate. That's why we're already seeing a coma and tail forming. But as it gets closer, the intensity increases exponentially, not linearly exponentially. Every time you halve the distance to the Sun, the radiation intensity quadruples. This is the tyranny of the inverse square law, and it's about to become very, very relevant. By early January, when C2024 G3 crosses Earth's orbit at 93 million miles from the Sun, the surface temperature will spike to around 200 degrees Fahrenheit. Water ice starts sublimating vigorously at this point. The comet will be venting thousands of tons of water vapour, carbon dioxide, and other gases into space every hour. The coma, that fuzzy cloud of gas and dust, will expand to potentially millions of miles in diameter, even though the solid nucleus might only be a mile or two across. You pull up the predictions from the Max Planck Institute for Solar System Research. Their models suggest that by January 10th, just 3 days before perihelion, C2024 G3 will be bright enough to see with the naked eye from dark sky locations. Magnitude 4 or 5, they estimate about as bright as the faintest stars you can see from a rural area, away from city lights. Then comes perihelion. January 13th, 2025, approximately 1500 UTC. You've got the time marked in your calendar with a red circle and about 15 exclamation points. At closest approach, C2024 G3 will be 8.3 million miles from the Sun's surface. To put that in perspective, that's about 0.089 astronomical units, or roughly 13 solar radii. The comet will be close enough that if the Sun were the size of a basketball, the comet would be passing about 10 feet away. The thermal environment at that distance is apocalyptic. Surface temperatures will reach somewhere between 3600 and 4000 degrees Fahrenheit, hot enough to melt most metals, hot enough to vaporize essentially every type of ice, hot enough to potentially crack solid rock through thermal stress. The Sun's radiation will be hitting the comet with an intensity about 14,000 times stronger than what we receive here on Earth. Dr. Matthew Knight from the USA Naval Observatory, who spent his career studying comets, describes this kind of close solar encounter in vivid terms. Imagine taking a snowball and throwing it into a blast furnace. That's essentially what we're watching, except the snowball is travelling at 400,000 kilometers per hour and the furnace is the Sun. Here's what happens during those critical hours around perihelion. The nucleus, let's assume it's maybe a mile across. We won't know for sure until closer observations will be losing mass at a catastrophic rate. The entire surface facing the sun will be vaporizing simultaneously. Jets of superheated gas will erupt from any structural weaknesses, potentially spinning the nucleus up to rotation periods of just minutes. The tidal forces are also significant. The sun's gravity at that distance creates a differential pull. The side of the comet facing the sun experiences stronger gravity than the far side. For a loosely bound rubble pile, which many comets are, this stress can be enough to literally pull it apart. It's the same force that creates ocean tides on Earth, but amplified to destructive levels. You remember comet Shoemaker-Levy 9, which got too close to Jupiter in 1992 and was torn into more than 20 fragments by tidal forces? Those fragments then crashed into Jupiter 2 years later, creating impact scars the size of Earth that persisted for months. Now imagine that kind of tidal stress combined with thermal vaporization, and you start to understand what C2024G3 is flying into. But here's the thing that makes this so exciting. Some comets survive these close encounters. Comet Lovejoy, officially designated C2011W3, passed just 87,000 miles above the sun's surface in December 2011, 10 times closer than where C2024G3 is headed. Everyone predicted total disintegration. And for a few hours, it looked like the predictions were right. The comet disappeared in the glare of the sun's corona as viewed by the SOHO spacecraft. Then, incredibly, it emerged on the other side. Battered, smaller, streaming gas and dust at prodigious rates, but intact. Amateur astronomer Terry Lovejoy, who discovered it and gave it his name, watched his comet survive what should have been certain death. The images of Lovejoy's tail stretching across the sky in the nights after perihelion were absolutely stunning, a ghostly white streamer visible to the naked eye from the southern hemisphere. So will C2024G3 survive? That depends on what it's made of and how it's put together. If it's a solid chunk of rock with just a surface coating of ice, it might make it through largely intact, though stripped of most volatiles. If it's a loose rubble pile, a flying sandbank as some astronomers call these structures, it could fragment into dozens of pieces, each following a slightly different trajectory out of the solar system. Or, in the most dramatic scenario, it could disintegrate completely in the hours around perihelion, creating a spectacular but short-lived dust cloud that briefly outshines everything else in the sky. Before dispersing into the solar wind, the spacecraft watching this unfold will have front-row seats to cosmic violence, NASA's Parker Solar Probe, which orbits the Sun specifically to study its outer atmosphere, will be in position to capture data. The Solar and Heliospheric Observatory SOHO, which has discovered over 4000 comets passing near the Sun, will track every moment. And the James Webb Space Telescope, with its infrared vision that can see through dust clouds, will observe the chemical signatures of whatever materials are vaporizing from the comet's surface. Dr. Carl Battams, who runs the Sun-Grazing Comets project at the Naval Research Laboratory, is practically vibrating with excitement. This is the kind of event that makes you grateful you went into astronomy. We're going to learn things about cometary composition and survival that we've been guessing at for decades. You mark your calendar again, January 13th, in just over a month. C2024G3 will either put on the show of a lifetime or vanish in a puff of cosmic smoke. Either way, the observations will be unprecedented. Either way, we'll learn something fundamental about what happens when an ancient visitor from beyond meets our star face to face. But before we watch that collision unfold, there's something else we need to talk about, something that's been nagging at the back of your mind since you first saw that irregular brightness curve, that asymmetric coma. those chemical signatures that don't quite match expectations. What if C2024G3 doesn't just fragment at perihelion? What if it fragments in a way that natural objects shouldn't? The coffee's gone cold again, you really need to start using an insulated mug, and you're staring at something in the fragmentation models that doesn't quite add up. When comets break apart, there are predictable patterns. Rotational stress creates fractures along structural weaknesses. Thermal expansion causes surface layers to crack and spall off. Tidal forces pull objects apart along the axis facing the gravitational source. It's messy, chaotic, but ultimately it follows the laws of physics in ways we understand. You pull up the data on 3I/Atlas again, the previous interstellar visitor that fragmented. The pattern was consistent with a loosely bound aggregate coming apart under solar heating, exactly what you'd expect from a rubble pile that had been gently assembled in the cold outer reaches of some distant planetary system. The fragments showed different levels of outgassing, different albedos, different compositions. It made sense. Nature is diverse like that. But then there's this nagging detail. One of the 3I/Atlas fragments showed a subtle acceleration that couldn't be fully explained by outgassing. The effect was tiny, just a few centimeters per second of velocity change, but it was there in the data, confirmed by multiple observation teams. Most astronomers attributed it to asymmetric venting from an irregular surface. Perfectly reasonable explanation. Except now you're looking at C2024G3's irregular brightness curve, and you're remembering Oumuamua's unexplained acceleration, and you're thinking about something that nobody wants to say out loud in professional astronomy circles. What if some of these objects aren't entirely natural before you start checking me for a tinfoil hat? Let's be very clear about something. The default assumption for any astronomical object is natural origin. That's not closed-mindedness, it's just basic scientific reasoning. We know natural processes can create bizarre things. We've seen binary asteroids, contact binary comets, asteroids with rings, moons with subsurface oceans, planets that rain diamonds. The universe is weird enough without invoking aliens. And this is a significant, but ignoring the possibility of artificial objects entirely is also unscientific. Because here's the uncomfortable truth: if technological civilizations exist elsewhere in the galaxy, and if even a tiny fraction of them send out probes or debris into interstellar space, then statistically speaking, we should encounter artificial objects occasionally. Dr. Abraham Loeb, who we mentioned earlier, calculated this in his book Extraterrestrial. If there is roughly 1 billion technological civilizations in the Milky Way, a conservative estimate based on current exoplanet data, and if just 1 in a million of them sends out probes over their history, that's 1,000 civilizations producing interstellar artifacts. Spread those artifacts across billions of years and trillions of miles, and the density might be low, but not zero. The odds might actually favour finding artificial objects over natural interstellar visitors in some scenarios. Think about it: natural objects escape their home systems through random gravitational interactions, rare events. But a technological civilization could potentially launch thousands or millions of probes deliberately. Is like the difference between finding a coconut floating in the ocean natural, but rare, versus finding a plastic bottle artificial, but common because we make so many. So how would we actually tell the difference? What would an artificial interstellar object look like? You pull up the checklist that SETI researchers use for evaluating potential technosignatures evidence of technology rather than biology. First item, anomalous acceleration without visible outgassing. Check, Oumuamua did that. Second item, unusual geometric shape with high aspect ratio. Check, Oumuamua again, with that cigar or pancake shape. Third item, non-gravitational acceleration not consistent with cometary activity. Triple check. But here's where it gets tricky. Every single one of those anomalies could have natural explanations. Frozen hydrogen venting invisibly, unusual structural formation, exotic ice behaviour. Nature is infinitely creative, and our models are imperfect. Dr. Amir Siraj from Harvard, who studies interstellar objects, puts it this way. The problem isn't that we can't think of natural explanations, we can think of dozens. The problem is that some of these natural explanations require pretty specific and unlikely conditions. At some point, you have to ask which is more unlikely, that natural processes created this perfect storm of unusual properties, or that we're looking at technology. Now let's talk about C2024G3 specifically. What would we need to see to seriously consider an artificial origin? Here's your checklist. Based on the scientific literature about technosignatures first, directed energy emissions. If C2024G3 suddenly starts broadcasting radio signals, especially in narrow frequency bands that don't occur naturally, that would be a massive red flag. The Breakthrough Listen project, funded by Yuri Milner to search for extraterrestrial intelligence, has already allocated observation time on the Green Bank telescope to monitor C2024G3 for exactly this reason. They're not expecting to find anything, but they'd be foolish not to look. Second, geometric fragmentation. If C2024G3 breaks apart and the fragments form suspiciously regular patterns, or if pieces separate with precisely matched velocities, that would raise eyebrows. Natural fragmentation is messy. Controlled separation, like a spacecraft deploying solar panels or shedding protective layers, would look different in the orbital mechanics. Third, unexpected maneuvers. If the comet's trajectory changes in ways that can't be explained by outgassing or gravitational perturbations, especially if those changes seem purposeful, like adjusting course to avoid too close solar approach, that would be extraordinary evidence demanding extraordinary investigation. Fourth, and this is the subtle one, information content. If we analyse the pattern of outgassing or the timing of brightness fluctuations, and find mathematical regularities that would be vanishingly unlikely to occur naturally, that could indicate deliberate signalling. It sounds far-fetched, but mathematicians have proposed that an advanced civilization might encode messages in the orbital parameters or physical properties of objects they send into space. Have we seen any of these things with C2024G3? Not yet. The acceleration is consistent with cometary activity. The brightness fluctuations are irregular in ways that match natural tumbling and asymmetric venting. The trajectory is hyperbolic, but that's explained by its interstellar origin. Everything we've observed so far screams normal comet as much as an interstellar visitor can be normal. And here's why astronomers are watching so carefully. We've only observed it for a few months. The really interesting data will come during and after perihelion. How it fragments, how those fragments behave, what spectroscopic signatures emerge as different layers vaporize, whether any pieces survive to continue on modified trajectories, all of that will tell us more about what this object truly is. Dr. Jason Wright from Penn State, who studies technosignatures and unusual astronomical objects, offers a balanced perspective. We need to be comfortable with uncertainty. C2024G3 is probably a natural comet. Probably, but probably isn't certainly. And the only way to move from probability to certainty is through careful observation and analysis. That means keeping an open mind while maintaining rigorous standards of evidence. You save the technosignature analysis and check the observation schedule. Multiple SETI projects will be monitoring C2024G3 through perihelion, not because they expect to find aliens. Expectation and preparation are different things, but because this is exactly the kind of opportunity you don't want to miss if something unexpected happens. And here's the thing that keeps you coming back to your computer at 3 a.m. Coffee in hand, staring at data plots, even if C2024 G3 is completely natural, even if every anomaly has a mundane explanation, we're still witnessing something profound. This object has travelled between the stars. It carries information about another planetary system, chemistry from another corner of the galaxy, perhaps even organic molecules that could tell us something about how common the building blocks of life are in the universe. But to extract that information, to really understand what we're looking at, we need more than observations from Earth. We need to think bigger about what it would take to actually reach out and touch these cosmic messengers while they're passing through our neighbourhood. Because the clock is ticking, and every interstellar visitor we encounter is an opportunity that might not come again for decades. Here's the frustrating reality that keeps planetary scientists awake at night. We have essentially zero ability to investigate interstellar objects up close with current technology. When Oumuamua was discovered in 2017, it was already past Earth, already on its way out. By the time scientists realised what they were looking at and started frantically proposing mission concepts, it was too late. The fastest spacecraft we've ever built, New Horizons, would have taken decades to catch up. And that's assuming we could have launched it in the right direction immediately, which we couldn't. It's like watching a once-in-a-lifetime concert from across the street through a foggy window because you don't have tickets. Frustrating doesn't even begin to cover it. But the experience with Oumuamua lit a fire under the aerospace community. Within months, researchers were publishing papers with titles like Project Lyra, sending a spacecraft to 1I/Oumuamua, and fast transit trajectories to interstellar objects. The European Space Agency assembled a rapid response task force called the Comet Interceptor mission, designed to launch to a holding position and then redirect to intercept comets or interstellar visitors with minimal warning time. You pull up the mission proposal documents. Comet Interceptor is scheduled for launch in 2029, which means it won't be available for C2024 G3. But the concept is brilliant. Park a spacecraft at the Sun-Earth Lagrange point 2, about 1 million miles from Earth, and just wait. When an interesting object comes through, fire up the engines and intercept it. The mission is designed to get close enough for detailed spectroscopy, surface imaging, and even direct sampling of the dust and gas coming off the comet. But even Comet Interceptor has limitations. It can only reach objects with relatively low excess velocities, things moving at maybe 10 to 20 kilometers per second above escape velocity. C2024 G3 screaming through the solar system at over 80 kilometers per second would be out of reach. You'd need something faster, more powerful, more ambitious. Enter Project Lyra, a mission concept that sounds like science fiction but is actually based on solid orbital mechanics. The idea: use gravitational assists from Jupiter and the Sun itself, a maneuver called an Oberth flyby, to accelerate a spacecraft to velocities high enough to catch interstellar objects. The researchers calculated that with current propulsion technology and clever orbital design, you could potentially reach Oumuamua within 26 years, arriving while it's still close enough to the Sun for solar panels to work. Dr. Marshall Eubanks, one of the scientists behind Project Lyra, describes the concept. We're not talking about Star Trek warp drives here. This is achievable with technology that exists today or is in advanced development. What we lack isn't the engineering, it's the funding and political will to move quickly when these opportunities arise. And that's the real problem. Isn't it space missions take years to plan, years to build, years to launch? The James Webb Space Telescope took over 2 decades from initial concept to launch. By the time you finish planning a mission to an interstellar visitor, that visitor is already long gone, fading into the cosmic distance where even our most powerful telescopes can't track it. What we need is a different approach entirely. Some researchers propose keeping a fleet of pre-built, ready-to-launch spacecraft on standby, like fire trucks waiting for the alarm to sound. The moment an interstellar object is detected, you calculate the optimal trajectory, load the mission parameters, and launch within weeks or months rather than years. Sounds expensive, it is. Estimates put the cost at several $1 billion for a standby fleet capable of reaching various types of interstellar objects. But consider what we'd gain the ability to collect actual samples from another star system, direct measurements of interstellar chemistry, close-up images of objects that formed in alien planetary systems. And yes, if we ever do encounter something artificial, the ability to investigate it properly rather than just watching helplessly as it disappears, Dr. Andreas Hein from the Initiative for Interstellar Studies makes a compelling economic argument. We spend billions on particle accelerators to study fundamental physics, billions on Antarctic research stations to study Earth's climate history. Why not spend comparable amounts to study objects that literally come from other stars? The scientific return could be revolutionary. But let's be realistic about the challenges. Even if we had a ready-to-launch spacecraft sitting on a pad right now, could we catch C2024G3? You run the calculations. The comet is currently moving at about 290,000 miles per hour relative to the Sun. After perihelion, that velocity will actually increase slightly due to the gravitational slingshot effect. To intercept it after it passes the Sun, you'd need to achieve similar velocities. The Parker Solar Probe, humanity's fastest spacecraft, tops out at about 430,000 miles per hour at its closest solar approach. That's fast enough in theory, but Parker achieves that speed by diving repeatedly toward the Sun in a carefully designed orbit, redirecting that velocity to chase an interstellar object departing at a different angle. The physics gets complicated fast. And the answer is probably not possible with that particular spacecraft. What about ion drives, nuclear propulsion, solar sails? Each technology offers different trade-offs between acceleration, fuel efficiency, and achievable velocity. An ion drive like the one on NASA's Dawn mission can run for years, slowly building up speed, but takes a long time to reach high velocities. Nuclear thermal propulsion offers high thrust but requires carrying heavy fuel. Solar sails are propellantless, but work best close to the Sun. The most promising concept for catching fast interstellar objects might be a hybrid approach. Use a solar sail to dive close to the Sun, building up tremendous velocity through the Oberth effect. Then deploy ion engines for fine-tuning the trajectory during the long coast phase. Researchers at Johns Hopkins Applied Physics Laboratory have sketched out missions using this technique that could theoretically reach speeds of 50 to 70 kilometers per second, fast enough to chase down most interstellar visitors. But here's the sobering timeline. Even if we started building such a mission today, it would take at least 5 to 7 years to design, construct, test, and launch. C2024G3 will be long gone by then, probably beyond the orbit of Neptune and fading from even our best telescope's view. This is the tragedy of interstellar object science. We're watching cosmic treasures pass through our neighborhood, carrying information that could revolutionize our understanding of planetary formation, organic chemistry, and perhaps even the prevalence of life or technology in the universe, and we can only observe them from a distance, like art students sketching a masterpiece they're not allowed to touch. Dr. Michelle Bannister, whose work on interstellar objects we mentioned earlier, captures the frustration perfectly. Every interstellar visitor is a sample return mission that delivers itself to our doorstep at no cost. Except we're not equipped to actually collect the samples. It's like having Amazon deliver packages to your house, but you don't have hands to open them. The good news: this is a solvable problem. Unlike faster-than-light travel or time machines, intercepting interstellar objects requires no new physics. No revolutionary breakthroughs, just engineering, funding, and the organizational will to build the right tools and keep them ready. Some nations and organizations are starting to take this seriously. The Chinese National Space Administration has published studies on rapid response interstellar object missions. Private space companies like SpaceX, with their emphasis on reusable rockets and rapid launch cadence, could potentially enable fast turnaround missions that weren't feasible with traditional aerospace. Jeff Bezos's Blue Origin has expressed interest in deep space science missions. The infrastructure is slowly coming together. What we need now is a detection network good enough to spot these objects earlier, giving us more time to respond, and the political commitment to actually fund and launch interception missions when opportunities arise. Because here's what keeps mission planners up at night. What if the next interstellar visitor is the one that shows undeniable signs of artificial origin? What if we detect radio signals, geometric structures, or impossible maneuvers, and all we can do is watch, because we never built the capability to investigate up close? That would haunt humanity for generations. But even without finding alien technology, even if every interstellar object we ever encounter is entirely natural, the scientific case for interception missions is overwhelming. And the clock is ticking not just for C2024G3, but for every future visitor that's already on its way, crossing the vast emptiness between stars, headed toward our tiny corner of the galaxy. While we can't physically reach C2024G3, there's another question worth asking: could it reach us? And more importantly, what does the existence of these high-speed interstellar objects mean for the long-term survival of life on Earth? You switch gears from mission planning to threat assessment, pulling up the databases maintained by NASA's Planetary Defense Coordination Office. Yes, that's a real office. Yes, the job is exactly what it sounds like, monitoring space for things that might hit Earth and figuring out what to do about them. Currently, the office tracks about 32,000 near-Earth objects, asteroids and comets whose orbits bring them reasonably close to our planet. Of these, roughly 200-300 are classified as potentially hazardous asteroids, or PHAs. That designation means they're larger than 140 meters across, and their orbits come within 4.6 million miles of Earth's orbit. Not necessarily on a collision course, but close enough that we keep a very watchful eye on them. Here's the thing: every single one of those 32,000 objects is a solar system native. We know their orbits. We can predict where they'll be decades or even centuries in advance. If one is headed our way, we'll have years or decades of warning. That's what makes planetary defense possible. You can't deflect what you can't predict, and you can't predict what you can't detect early enough. Interstellar objects completely break that comfortable predictability. Dr. Lindley Johnson, former planetary defense officer at NASA, addressed this in a 2019 briefing after Oumuamua interstellar objects represent an unknown factor in planetary defense. They approach from directions and at velocities we're not optimized to detect. Our current survey systems are designed to find objects in solar orbits, not hyperbolic trajectories from beyond the solar system. Let's run a worst-case scenario. Imagine an object like C2024G3, but instead of passing millions of miles from Earth, its trajectory intersects our planet at 290,000 miles per hour. How much warning would we have? You plug the numbers into the impact probability calculator. Assuming perfect detection capability, which we definitely don't have, we might spot such an object when it crosses Jupiter's orbit, about 460 million miles from Earth. That's C2024G3's speed. That gives us roughly 66 days of warning, 2 months to confirm the trajectory, calculate the impact location, and, well, That's where it gets complicated. Our current planetary defense strategies rely on either kinetic impactors, spacecraft that slam into asteroids to nudge them off course, or, in more advanced concepts, nuclear deflection devices. But those techniques require time. The DART mission Double Asteroid Redirection Test, which successfully deflected the asteroid Dimorphos in 2022, was launched 10 months before impact. The asteroid was moving at a relatively sedate 15,000 miles per hour. An interstellar object moving nearly 20 times faster, the kinetic energy involved is proportional to the square of the velocity. Trying to deflect something moving at 290,000 miles per hour would require hitting it with a much more massive impactor, or hitting it much earlier in its trajectory, or using a nuclear explosive, and even then, the physics gets complicated fast. Dr. Brent Barbee from NASA's Goddard Space Flight Center ran simulations on this exact scenario. With current technology, if we detected an interstellar impactor with less than 90 days of warning, our options would be extremely limited. We might be able to fragment it with a nuclear device, but that creates other problems. Now you potentially have multiple impacts instead of one. The good news: the odds of an interstellar object hitting Earth are vanishingly small. Space is incomprehensibly vast, and Earth is incomprehensibly tiny. Think about trying to hit a specific grain of sand on a beach while throwing from a mile away. Now make that beach the size of a continent. That's roughly the scale we're talking about. Statistical models suggest that an interstellar object with a diameter over 100 meters might impact Earth once every 500 million to 1 billion years. Smaller objects, say 10 meters across, might hit every few 100,000 years. For comparison, solar system asteroids in that size range hit Earth roughly every 1,000 years, so interstellar objects are a much smaller threat than homegrown space rocks. But here's what makes planetary defense experts nervous. Those statistics assume interstellar objects are distributed randomly through space, moving in random directions. What if they're not? Consider this: if an interstellar object's trajectory brought it into our solar system, that trajectory was determined by whatever gravitational interactions ejected it from its home system. Most likely, it was a close encounter with a giant planet something like Jupiter, but in another star system that flung it into the galaxy at high speed. Now, here's the subtle point: gravitational ejections aren't entirely random. They depend on the architecture of the planetary system, the masses and orbits of the giant planets, the angle at which the ejected object approached them. Some trajectories are more likely than others, which means some regions of the galaxy might be receiving more interstellar debris than others. Are we in one of those regions? Nobody knows. We've only detected 3 confirmed interstellar visitors, and you can't establish statistical patterns from a sample size of 3. But the question keeps popping up in academic papers with titles like "The Anisotropic Distribution of Interstellar Objects" and "Preferential Ejection Channels in Multi-Planet Systems." Dr. Amaya Morrow-Martin from the Space Telescope Science Institute, who's done extensive modelling on this, puts it bluntly: we're flying blind. We don't know if interstellar object encounters are truly random, or if there are patterns we haven't detected yet because our observation time is so short. It's like trying to understand traffic patterns by watching an intersection for 5 minutes. Then there's the really unsettling possibility: directed objects. We spent time earlier discussing whether some interstellar visitors might be artificial. If they are, and that's still a massive if, then their trajectories might be deliberately aimed at planetary systems, not necessarily at Earth specifically, but at star systems known to have habitable planets. How would an alien civilization even know which stars have planets? Well, the same way we know by detecting the subtle wobbles in starlight caused by orbiting planets, or the tiny dimming when planets pass in front of their stars. Those signals travel at light speed, so any civilization within a few hundred light years could potentially know that our sun has a system of planets, including at least one in the habitable zone. Would they send anything our way that's entering the realm of speculation built on speculation? But it's worth noting that several SETI researchers have proposed that interstellar objects might be deliberate probes, either still functional or ancient derelicts sent out by technological civilizations for exploration or communication purposes. Dr. Zaza Osmanov from the Free University of Tbilisi published a paper calculating that if just 0.1% of stars in the galaxy host civilizations that send out probes, there could be up to 10,000 artificial objects in our solar system at any given time. Most would be small, inactive, or in orbits that keep them far from Earth. But statistically, we should encounter one occasionally. Is C2024G3 one of them? Almost certainly not. Is the next interstellar visitor we detect? Probably not. But almost certainly not and probably not aren't the same as definitely not. And that gap between probability and certainty is precisely why astronomers are watching these objects so carefully. Here's what we know for sure: we're not ready. Not ready to intercept interstellar visitors for scientific study. Not ready to deflect them if they pose a threat. Not ready to properly investigate them if they show signs of artificial origin. We're in the position of coastal villagers watching distant ships sail past, unable to reach them, unable to signal them, only able to watch and wonder where they came from and where they're going. But unlike those villagers, we have the technology within reach to change that situation. What we need is the collective decision to actually build the systems we've designed on paper: better detection networks, rapid response spacecraft, international coordination protocols for when interesting objects are discovered. Because one thing has become abundantly clear from the arrival of Oumuamua, 2I/Borisov, 3I/Atlas, and now C2024G3, these visitors aren't rare cosmic flukes. They're regular occurrences that we simply never noticed before because we weren't looking properly. And now that we're looking, now that we know they're out there, we can't unsee them. The question isn't whether more will come, it's how we'll respond when they do. It's late December now, and you're watching the observation window narrow with each passing day. C2024G3 is getting brighter, easier to spot even with modest amateur telescopes, and the data is pouring in from observatories around the world. Every night brings new images, new spectra, new measurements that add pieces to the puzzle of what this cosmic visitor truly is. The global astronomy community has mobilized in ways you've rarely seen. Professionals and amateurs alike are coordinating observations, sharing data in real time through platforms like the Astronomer's Telegram and the Minor Planet mailing list. There's something beautiful about watching scientists from dozens of countries, some of whose governments aren't exactly friendly with each other, collaborating seamlessly because they all recognize this opportunity won't come again. Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics coordinates much of this effort. What we're witnessing is citizen science at its finest. Amateur astronomers with backyard telescopes are contributing data that complements observations from billion-dollar space telescopes. Everyone has a role to play in understanding these objects. But here's what strikes you as you scroll through the latest observation reports. We're still basically guessing about fundamental properties of C2024G3. Its exact size unknown estimates range from 0.5 mile to 3 miles across based on brightness and assumptions about reflectivity. Its rotation period, unclear. The brightness variations suggest it's tumbling, but the pattern is irregular enough that pinning down a specific rotation rate is difficult. Its composition. We've got spectroscopic data showing various ices and organic compounds, but the exact ratios and what that means about its formation environment remain subject to interpretation. After months of observation and millions of dollars in telescope time, we still can't definitively answer basic questions like how big is it or what's it made of. That's the frustrating reality of studying objects that are millions of miles away and moving too fast to reach. This is precisely why the next generation of survey telescopes is so crucial. The Vera C. Rubin Observatory in Chile, scheduled to begin operations in 2025, will revolutionize our ability to detect interstellar objects. With its 8.4-meter mirror and massive camera, it will scan the entire visible sky every few nights, spotting faint, fast-moving objects that current surveys miss entirely. Dr. Mario Jurek from the University of Washington, who works on the Rubin Observatory project, estimates the impact. We expect to detect somewhere between 1 and 10 interstellar objects per year once Rubin is fully operational. Maybe more. Our statistical models are based on a sample size of 3, so there's huge uncertainty. But conservatively, we'll see more interstellar visitors in the first 5 years of Rubin operations than we've seen in all of human history before it. Think about what that means. Instead of being surprised by the occasional interstellar visitor, we'll have a catalogue of them. We'll be able to compare their properties, look for patterns in their trajectories and compositions, understand whether they cluster in certain regions of the sky or arrive from random directions. We'll finally have enough data to move from anecdotes to statistics, from look at this weird object to here's what interstellar populations tell us about galactic planetary system formation. But Rubin is just the beginning. NASA's NEO-Surveyor mission, scheduled for launch in 2027, will use infrared observations to detect asteroids and comets that are dark and hard to spot in visible light. Some interstellar objects might have extremely low albedos, essentially tar-black surfaces that barely reflect any light, making them nearly invisible to optical telescopes, even when they're close. Infrared detection bypasses that problem by detecting the heat the objects radiate. There's also serious discussion about deploying a constellation of small satellites in various orbits around the Sun, specifically to watch for interstellar objects from multiple vantage points. Parallax observations comparing how an object appears from different locations would let us pin down distances and trajectories much more precisely than we can now. The European Space Agency's Comet Interceptor mission, which we mentioned earlier, represents another leap forward. Scheduled to launch in 2029 and wait at a gravitational parking spot for an interesting target, it will finally give us the capability to actually visit one of these objects up close. Not C2024 G3, that ship has literally sailed, but the next one, or the one after that. And here's something that doesn't get talked about. Enough private space companies are increasingly interested in this field. Asteroid mining companies see interstellar objects as potential resources after all. They're already on trajectories that bring them close to Earth. No expensive rendezvous maneuver needed if you catch them at the right time. Some contain water ice, useful for life support and fuel. Others might have rare minerals or organic compounds worth studying or even extracting. Is it weird to think about mining an interstellar visitor? Maybe. But it's also pragmatic. If we're going to build the infrastructure to intercept these objects anyway, we might as well design missions with multiple purposes: scientific investigation, resource utilization, and yes, checking to make sure they're not artificial probes all serve humanity's long-term interests. Dr. Philip Metzger from the University of Central Florida, who studies space resource utilization, makes an interesting point. Every interstellar object that passes through our solar system represents free delivery of materials from another star system. From an economic standpoint, that's remarkable. From a scientific standpoint, it's invaluable. We should be treating these objects as the cosmic treasures they are. So what happens next? The immediate answer is simple. We watch. On January 13th, 2025, CEC 2024 G3 will make its closest approach to the Sun, and every major telescope that can possibly observe it will be pointed in that direction. Space-based observatories like SOHO and Parker Solar Probe will capture the event from angles impossible to achieve from Earth. Amateur astronomers will stream it live on YouTube. Scientists will be analysing data in real time, looking for anything unexpected. Will it survive? Will it fragment? Will it produce a spectacular tail visible to the naked eye? Will it do something completely unexpected that forces us to rethink our models? Nobody knows, and that's exactly what makes this exciting. But the bigger answer, the one that keeps you up at night with equal parts anxiety and anticipation, is that C2024 G3 is just the beginning. It's the fourth confirmed interstellar visitor in 7 years. Given improvements in detection capabilities, we'll probably see the 5th one within a year or two. The 10th one maybe by 2030. The 100th probably within your lifetime. Assuming we keep building better telescopes and dedicating resources to this search. We're living through a unique moment in human history. For hundreds of thousands of years, humans looked up at the night sky without any idea that objects from other star systems were occasionally passing through our cosmic neighbourhood. Now, suddenly, within just the last few years, we've confirmed they exist, watched several of them transit our solar system, and begun designing missions to intercept future visitors. This is what it feels like to be at the frontier of discovery. Not the discovery of something we expected to find. We've been doing that kind of science for centuries. No, this is the discovery of something we didn't even know to look for. Something that opens up entirely new fields of study, new questions we never thought to ask. What's the chemical composition of planetary systems around other stars? How common are organic molecules in the galaxy? Are there patterns in how planetary systems eject debris? Do some regions of space send more visitors our way than others? Could we detect artificial objects if they pass through? What would we do if we did? These aren't hypothetical questions anymore. They're research programs waiting for funding, missions waiting to be designed, discoveries waiting to happen. And somewhere out there, in the vast darkness between stars, the next visitor is already on its way. Maybe it's a pristine comet from a young star system, carrying chemistry that hasn't been seen in our solar system for billions of years. Maybe it's a fragment from a shattered planet, bearing evidence of violent collisions in distant planetary systems. Maybe, just maybe, it's something we've never imagined. Something that will change everything we think we know about our place in the universe. The only certainty is this: it's coming. And when it arrives, we need to be ready not just with better telescopes and faster spacecraft, but with the curiosity, openness, and scientific rigour to understand what we're really looking at. Because the universe has just started sending us messages in bottles from distant shores. The question isn't whether we'll keep receiving them. The question is whether we're prepared to read what they're telling us.